Okay, this is going to be the video for section 5.1 for differential equations, which is modeling real-world scenarios using higher-order linear differential equation models. We could look even at nonlinear models, but this is already complicated enough. So for our course, we're going to just do section 3.1 was on first-order linear. Section 3.2, we looked at just a couple of examples of second-order first order nonlinear differential equations, and we're going to do section 5.1, which is second and higher order derivatives, but sticking with linear models. Okay. It gets more and more complicated as we go into nonlinear models, so we'll cut it off here. Having a second or higher order derivative or differential equation, that opens up the possibility for modeling an even greater range of scenarios than the first order differential equations. They get more complicated as we add order, right? Or if we go to nonlinear. So we only have time here in the class to focus on a couple of scenarios. But these particular scenarios we're going to talk about are really, really important in physics and engineering. We're going to talk about vibrations by considering a mass spring system, which is the foundation for all physical vibrations. So everything we know about vibrations and about things that involve sinusoidal behavior are essentially modeled using this as its core. And then we're going to see how that vibration has an analog in electrical circuit theory. So just between those two things, we'll just be able to look at the foundation of a lot of models in physics and engineering. All right, so we're going to start with the simplest physical vibration system we can, which is a mass hanging on a spring in a gravity field. Okay, so first of all, springs are subject to something called Hooke's law, and that just means that if you deflect a spring, then as long as you stay within the non-deformation region of the spring where you don't permanently deform it, then the spring will exert a force that's directly proportional to the amount that it's being stretched. And that's called Hooke's law. If you picture the situation this way, let's imagine that you had some ceiling or something and you had a spring that starts out with some unstretched length L, right? But then you hang a mass from it, which is being acted upon by gravity that's downward in this picture, right? So it's pulling the string and it's displacing it a distance s, which is what we call to equilibrium position. So, it just, if you leave it there and let it just kind of sit there until it stops moving, right? It's displaced s further downward from its initial unstretched length. Then we're going to define a coordinate system where downward is positive. So if I then further pull the spring even further down, so it stretches even more, I'm going to add a distance x. So our displacement distance is going to be x, and that's how far we're moving away downward from the equilibrium position, right? So at the equilibrium position, it's going to be that the force of gravity is perfectly balanced by the spring force, right? But if we then further displace this further, that's going to be positive x in this direction, and negative x would be up here, and x is 0 when we're at the position where it's just naturally hanging. So we're usually interested in this position of mass over time. So we're going to find a differential equation which uses x as its dependent variable, and then t is the independent variable. So we can find how x changes with time. Okay. All right. So it turns out that any force that stretches a string, as long as you stay within the non-deformation region, then the amount of stretching is well modeled using Hooke's law, which says that the force is just proportional to the amount of displacement. Okay. So at equilibrium, where the only force is acting is gravity, which is mass times gravitational constant, that means that the force from gravity is balancing the force from the spring. So mg is equal to ks. Okay. All right, so that's what happens when the spring is just sitting there. If we further disturb the system by then pulling it, let's say in the positive direction to string more, then eventually the behavior of the mass has to follow Newton's law, which is F equals ma. So that means the sum of all the forces is going to be equal to the mass times the overall acceleration of the object, right? So we could write it this way, that the mass times the acceleration has to equal the sum of the forces, right? So right now I have mg, which is acting in the positive direction. That's the force of gravity here. That's one of the forces. And then the other force is the spring constant, which is acting in the negative x direction because it's opposing the motion of the gravity. So it's negative k. And the amount that it's stretching is the initial displacement s from equilibrium from the unstretched length. So the spring starts out with no force. The weight of it itself, Ks, is on there. And then there's also the additional displacement. So we're displacing from the unstretched length. S is how far it hangs naturally plus how far we pull it. So S plus X is the displacement times the spring constant K. And this would be the basis of, this is just a F equals ma equation. Sum of forces equals mass times acceleration. All right. But then we know that acceleration is the derivative of velocity, and velocity is the derivative of the distance. So that means acceleration is the second derivative of the distance, right? So the second derivative of x with respect to t times the mass has to equal this right-hand side, which is the sum of forces. So if you multiply out this k, right, then you can bring this term over here to the left side, and you get that m times the second derivative of x plus k times x is equal to the spring constant times the initial displacement, the equilibrium displacement s, plus mg. But because at equilibrium, the force of the spring is balancing the weight of the object, then that means that that Ks is equal to mg, and therefore, if we take negative Ks, so I could substitute an mg in here. So this would be negative mg plus mg, which means this is 0. So the equation for this mass spring system is that the mass times the second derivative of x with respect to t plus the spring constant k times x has to equal 0. And the force of gravity here is canceled out by the initial displacement, okay? So this right here is a differential equation, a second order linear differential equation of free undamped motion of mass on a spring. We'll talk about what these terms mean as we move throughout the lesson here. Okay, so before we solve this differential equation, it's helpful to divide by the leading coefficient. So we'll get that the second derivative plus k over mx equals 0. And then it's helpful to introduce this particular symbol substitution. So we're going to replace the symbol k over m, that constant, with the constant omega squared. And we'll talk more about the meanings of these things later. So we'll write it in this form. And then this is a linear second order differential equation. So I could solve this using an auxiliary equation because I have constant coefficients. So m squared plus omega squared equals 0. This is a constant. So m is going to end up being negative omega squared. And since this is a positive value here, this means we're going to be taking a square root of a negative. So we're going to get complex, in fact, purely imaginary numbers here for the two auxiliary equation roots, plus and minus omega I, when we take the square root of this, okay? So alpha is 0, and that means that our solution is x as a function of t, displacement of the spring as a function of t downward, is equal to some constant times the cosine of omega t plus some constant times the sine of omega t. Okay, so this is the solution to this differential equation here, which represents the mass on a spring when it's just hanging down and then subject to some initial displacement. Okay, interestingly, this solution with one cosine and one sine term, you would think it would look really complicated, but the truth is that if you actually graph this out for any constant C1 and C2, it turns out to look like a single sine wave. Let me show you that with this GeoGebra thing, which you can play around with if you want on your own here. Here, this blue curve is this constant A times cosine. So this is a cosine wave that starts out at its max and then goes down at t equals 0. And then this red here is a sine wave, right, that has a constant here. I'll move it out here like this. But this green wave is just, it's just what's in the lesson here. It's some constant times the cosine plus some different constant times the sine. And the argument is the same. So these are programmed to be the same. Interestingly, when you add this blue wave and this red wave, it produces another wave which is not complicated looking. It just looks like another sine wave, right? What happens when you change the multipliers, though, is that not only does the magnitude change of this, right, but notice that it's shifting around. So the phase shift also changes, okay? So not intuitively, but true, if you take a constant times a cosine of some argument plus a different constant times sine of the same argument, because these are shifted 90 degrees in phase, that produces a new sine wave that has a magnitude A and that same frequency, or that same term here, but plus a phase shift, phi. And the equations that allow you to solve for these is this A turns out to be the square root of the sum of the squares of these two. And the tangent of this phase shift angle turns out to be C1 divided by C2. If you want to prove this to yourself, you can show that this is true by using trig identities. Over here, you can do A times sine of U plus V and look up the sign of a sum and expand that out, and then also figure out what happens over here, and you'll be able to show that when these are as specified, this side equals this side. Okay, so when we write a solution like this, x of t, the displacement is, you can either write it with the separate terms, or you can write it with a single sinusoid of the single term, but that will include a phase shift that combines these terms like this. All right. Okay, so these meanings have context. So let me look at the combined version here. Right? Since this is a sine wave, we know sine goes through its entire cycle when the argument of it goes from 0 to 2 pi. So if you take omega t plus phi and make that go from 0 to 2 pi, I could first subtract off the phase shift in all three locations, and then I can divide everything by omega. And that means that this cycle will start at negative phi over omega when time is at negative phi over omega, and it'll end at 2 pi over omega minus that. So that means this phi over omega is the phase shift, how much this is shifted from the starting point of the sine wave. So right now the phase shift is somewhere over here, right? Because actually it would be a negative because the sine wave starts, or right here, because the sine wave starts at 0 and goes up. So this distance here is a phase shift, right? And then the 2 pi over omega is the period, which is the distance between the same point on the curve. So from here to here is the period. How much time elapses from crest to crest or from trough to trough. Okay, so the period, which a lot of times you use capital T for, is this value here, 2 pi over omega. And that's the time between crests on the wave, right? I can show you down here. The period is that, okay? The phase shift, which is phi over omega, happens to be the time after 0 when the first zero crossing occurs. So I didn't quite draw this here. Actually, this would be over here. This is the phase shift. In fact, actually, it would be here because it's when we start going up. Sine goes positive. So correction in the notes, this is the phase shift right here because this is where the sine wave starts. Okay, and then the amplitude is just the total amplitude above or below the baseline that the wave is waving. And then the frequency is 1 over the period, so it's 2 pi divided by omega, which is omega over 2 pi, which means if you solve this for omega, omega is 2 pi times the frequency. Now the frequency is the number of cycles per second, so if you counted off 1 second of time, it would be how many complete cycles occur in that time. This omega constant is actually, or it's actually a variable here of this frequency, it's 2 pi times the frequency. Sometimes that's called the circular frequency, or some engineering books call this the angular frequency. It's very frequently used in engineering just so that we don't have to keep copying 2 pi's all over the place. So when you have this here, you can think of this as 2 pi times the number of cycles per second times t. So rather than writing 2 pi f all over the place, we just write omega. All right, so when we release this, if we take a spring and we pull it down and we release it, it's going to bob up and down. And if you plot its position over time like this, it's going to form a sine wave, right? Which sort of makes sense, right? If you displace this and let it go, it will move up and down, and the position x will trace out a sine wave versus time, right? Remember that downward is the positive direction, so this is positive. Okay, because there's no other forces acting on this mass, there's no air resistance that we're accounting for, there's no loss of energy due to friction heating up the spring, where this is a perfect model, then this motion would theoretically occur forever. In other words, once you release this, it would go up and down just like this forever, with no attenuation, no dampening at any time. Okay, but of course, in the real world, there's other forces acting on the mass. Some energy is lost to heat in the spring. There's air resistance, stuff like that. So the oscillation amplitude will slowly decrease over time until finally it returns to its equilibrium position. The way this is modeled is to include something called damping. That's the official term for it. And that is, it's sort of like air resistance for when we consider motions of falling masses. It's just something which opposes the motion of the mass in a similar way to the way air resistance opposes it. So you can imagine that you took your mass and yes, it's moving up and down, but we're putting the mass inside of a thick liquid so that this motion is being opposed by something, right? That's it's heating up this liquid as it moves, so some of the energy is being removed from the system, something like that. So what we do is we just say that just like with air resistance, we're going to have some term which has a constant of proportionality times some derivative or value of the of how fast the thing is moving. Remember with air resistance, we said it's either minus kV or it's minus kV squared, where this is the how fast the object is moving through the air. It turns out that for spring motion, well, for air resistance, this was the right model. Air resistance does vary as the square of the speed. For spring motion, it turns out that the better model is the linear proportion. So what we do is we just take a proportionality constant. We've already used k for the spring constant, so we change this k to a beta. We use beta for the damping constant. And then the velocity, the speed of motion, is the first derivative of displacement. So we have a term here which is minus kv, but the v is dx dt, and we have to use a different symbol for the constant. And so if you move these both to the other side, well, you can think of it this way. This is ma equals a force from the spring plus a force from damping, right? And then each of these terms are adding to the things that affect the acceleration of the object. So typically, since these are both opposing motion, they're both negative terms, so we bring them to the other side and make them positive. And this is the form of differential equation that's most useful when you're trying to set up a mass spring problem. So I usually go to this form first, and I fill things in and then use this as the basis of solving. All right, so I've got mass times the second derivative plus beta, which is the damping constant, times the first derivative of distance versus time, plus the spring constant times just the displacement equals 0. Okay, and the reason why we're not seeing a term in here for the gravity is because the gravity got canceled out because of the spring constant balancing the force. If you go back to the first slides. All right, so that's our differential equation. So again, as we solve this, it's going to be useful to make some symbol substitutions. So first we'll divide by m, and we'll get that the multiplier for the first derivative is beta over m. That is typically relabeled 2 lambda. Okay, and then this k over m constant is again called omega squared. So we have a new constant here, lambda, where 2 lambda is defined as the damping constant over the mass. Okay, and that means we have a second order linear differential equation with constant coefficients. So I can use an auxiliary equation to solve, and we're going to have to use the quadratic formula to solve this time. So the roots of the auxiliary equation would therefore be negative lambda plus or minus the square root of lambda squared minus omega squared. Because we have a possibility of this either being this discriminant being either 0 or positive or negative, we have 3 cases. But in every case, the general solution is a constant times e raised to that plus a constant times e raised to that. Okay, so let's look at the 3 cases. The first case would be if the discriminant is positive. So if we have lambda squared minus omega squared is positive, then that means we're going to have a real number, right? Our solutions are going to be negative lambda plus square root of some positive number, and then negative lambda minus that. So this will just be a real number and another real number. And that means that the shape of the form of this is going to basically be just exponential decay, right? And so this particular situation is called overdamping. And it basically means there's no oscillation. The position where we start from just slowly moves to align to some equilibrium position, right? Where we're back to the x0, which means we're at the equilibrium hanging level. Okay, it might undershoot slightly, but it'll come back, or it moves just slowly to there. Okay, so we'll have that. That is if we have a positive discriminant in our auxiliary equation for this. If this is positive, okay, the inside is positive. Okay, the second case would be if the inside happens to be 0. If omega squared and or lambda squared and omega squared are exactly equal, where this is 0, then we have, this is 0 here, so we're just going to have e to the negative lambda t plus, now we can't just use e to the lambda t again, so since we have a repeated root, we have to use the t times that. Remember, we added an extra x variable, so in this case it's t. This particular situation is called critically damped, and physically it means we're right on the verge of being allowing an oscillation to occur, but it more rapidly approaches equilibrium. So here it might take a long time to approach equilibrium, right? But here we're moving as quickly as possible to the equilibrium level, right? Or it might look like it's beginning to oscillate, but it will move to equilibrium before it gets a chance to complete one complete oscillation. So that is called critically damped. Okay. The third possibility is if in the roots the discriminant is negative, and so if we get negative, then we're going to have a complex number, alpha plus or minus beta I, because this will be a negative number, and that means we have the most general form of the solution where you have a negative exponential from the real part, and then you have also a complex number, so you have cosine of that t plus sine of that t. This particular situation is called underdamped, and it physically means that the damping isn't strong enough to prevent this from oscillating before it reaches equilibrium. So if you have really light damping, it might oscillate for quite a while before eventually this term here starts to cause it to go towards the equilibrium position of 0, right? On the other hand, if this damping is lighter, or heavier, sorry, if this damping is heavier, it might only oscillate for a couple of cycles before, right? But whatever that envelope is determined by this term here. So you have oscillatory behavior, and the amplitude is being slowly attenuated here by having a negative exponential multiplier. Okay, so these are some possible displacement curves for underdamped mass spring systems. All right, so far we've just been finding the general solution to these spring systems. Okay, when we actually solve a problem, which we'll have you just jump in and try it here, we will have to figure out what those constants are, and typically we need to have initial conditions. So since there's two constants, a lot of times we're told something about the initial displacement, like we might have a problem that says the mass is initially pulled 1 foot below the equilibrium position, which is equivalent to saying that x at time is 0 is positive 1, because remember, pulling down is positive. Or we might say the mass is released 2 feet above the equilibrium, so we push the spring upward and then release it. That means that we're adding an initial negative displacement, so at t equals 0, x is negative 2. Since there's a second constant, we usually also have to have information about the derivative. And that means that not only are we just pulling the spring and releasing it, but instead of just letting the mass go, maybe we're actually throwing the mass. So it has additional velocity besides what the spring is imparting. So this would be shown in a problem like this. It might say the mass is released with an initial velocity upward of 3 feet per second. That's equivalent to saying that the first derivative of x at time 0 is negative 3. Negative meaning upward, which is the negative displacement direction. So once we have our general solution, we just plug in these initial conditions to solve for C1 and C2. Okay, so that is an analysis of just a freely moving spring. We take it, it hangs from the ceiling at a place that's where its weight and the spring force are balanced in equilibrium, and then we displace it and possibly impart an initial velocity and let it go, but then we just let it freely move, and the solution to the differential equation shows its position over time, up and down. Okay, so that's called free motion. Now, the other possibility is we can drive the spring, which means once we set it in motion, we don't just let it go forever. We also, either at regular intervals or continuously, we impart additional force to the mass in some way. Like maybe the whole ceiling is moving up and down so that there's an additional force that's being applied on the spring, or we're blowing on the like something that's imparting either magnetic current or air is being used to blow the mass with wind at the same time as it's also oscillating. So when we do that, that means we have what's called a driven system. And the way that is shown in the differential equation is we used to have our differential equation equal 0, But now we have what's called a driving function on the right-hand side. So if the right-hand side is not zero, it means we're applying a force besides just gravity and the spring constant. And so that's modeled by putting a force that varies with time over here. So now this becomes a non-homogeneous equation, which means after we solve the characteristic equation, we have to use either separation of variables or undetermined coefficients to guess a particular yp from a table to get the complete general solution with the non-homogeneous part of it. Okay. So before we solve, we typically do go ahead and divide by m to get these in this form. So we have second derivative plus 2 lambda, where that's beta over m first derivative, plus k over m, which is rewritten omega squared. And then we have this driving function, but divided by m, which is represented usually by a capital F of t. Okay, so divide by m first, and then you solve the characteristic corresponding homogeneous equation, and then you use some method to add on the particular solution for the driving function. All right. All right, so when you do that, and you'll see this when you do the homework problems, you'll end up typically with a solution with some terms that came from the homogeneous part, plus some terms from the specific solution, or the particular part, right? The YP. And some of these terms will have exponentials that have a negative constant times t, which means that as time goes on, eventually these terms drop out. They fade away. But some of the terms don't have that. They just continue to oscillate. So the terms that drop out are referred to as transient terms, or the transient solution. And the terms that stay there even after the transient terms have disappeared are called the steady state terms, or the steady state solution. So if you were to take, this is actually a solution to one of the problems, I believe, in the homework, but a typical problem, then you would have some transient terms and the steady state terms that all apply starting at t equals 0. And so you can see a complicated waveform here. That's because you have 4 different sinusoids all being added, right? These two together do look like a single sine wave with a phase shift, right? But that's at frequency t. Plus, so omega t plus some phase shift, right? And these two are also representing something like a single sine wave, right? But this time it's with a different angular frequency and phase shift. So when you add the two together, you get a more complicated waveform. But eventually, as these terms drop out, it starts to settle down to just a single sinusoid, which is built from the 2 steady state terms. Okay, so there's a period of time when all the terms, including the tangent terms, are affecting the signal or the position, and then eventually all the transient terms drop out and it smooths out to the steady state. So it just basically matches the driving function, right? After a while, the spring will match the driving function. Okay, so what is going on those transient terms? Okay, well, in this particular point, right, the transient terms, the driving function has a circular frequency of 1, but the transient terms have a circular frequency of 3. That particular frequency is called the system's natural frequency, because it means if you weren't driving the system, you just release the mass and let it, flop around, oscillate, it will oscillate with some natural frequency that's mainly determined by the spring constant, right? So that's called the natural frequency. And it turns out that something really interesting happens if you try to drive the system with a driving function that's at the natural frequency, especially in systems with no damping. Okay, so if you have no damping and you drive a mass spring system at its natural frequency, what would happen? Here's a specific example. Let's say we have a mass of 2 kilograms that's attached to a spring with a spring constant of 32 newtons per meter. It comes to rest at equilibrium. Starting at time t equals 0, a driving force is applied. F of t is 16 cosine of 4t is applied to the system, so it has a circular frequency of 4. Find the equation of motion in the absence of damping. So we would start with our general equation here, which is mass times the second derivative plus beta times the first derivative plus k times x equals the driving function. And then we fill in what we know. We have a 2 kilogram mass. This is expressed already in mass terms. The damping, it was said there's no damping, so the damping constant would be 0. The spring constant that we were told is 32, and we have our driving function. So this, if we divide by the mass, we get that, divide everything by 2, we get x double prime plus 32 divided by 2 is 16x equals 8 times cosine of 4t. So first we would set this temporarily equal to 0 and solve the homogeneous equation. We can do that with an auxiliary equation. M squared plus 16 is 0. That means we're going to get imaginary roots here. So we have plus and minus 4i. And so that means that the homogeneous solution is a constant times cosine of 4t plus a different constant times sine of 4t. Okay, and then we would solve the non-homogeneous equation. We could use the undetermined coefficients, look it up in a table method, right? And if you looked up the right-hand side, something times cosine of 4t, it suggests that the particular solution would be a constant times cosine of 4t plus a different constant times sine of 4t. But if you try to take the derivatives and plug that in, you're going to find that you can't solve for a and b. And the reason why is this cosine of 4t and sine of 4t look just like terms here, so they're getting absorbed. So instead, whenever we have absorption happening, we just go ahead and multiply by an extra x variable, which in this case is t. So the particular value actually, or solution, postulated solution, is a some constant times t cosine 4t times or plus b times t sine 4t. And when you take the first and second derivatives and plug it into the differential equation and you solve for a and b, I'm omitting the steps here, it turns out that a is 0 and b is 1. So the particular solution turns out to be t times 4 of sine of 4t. So if I add that in with the YC, the homogeneous solution, then I get this as the general solution. Okay, and then we have some initial conditions. So we didn't specify it up here, but let's see. It does come to rest at equilibrium. So at t equals 0, we have some initial displacement. Let's go ahead and impose some initial conditions here to continue the problem. So let's say that I'm displacing this 1 meter downward at time 0, and I'm also throwing it downward with 2 meters per second initial velocity. So if I had that given as the problem, I could plug in, I could take the derivative of this, right, which would be this. Remember on this one, we have to use product rule. So first times derivative of the second plus second times derivative of the first. That's why there's two terms here. And then I could plug 0 in for t and 1 in this equation and get an equation for C1 and C2. And then I could use this x, or this t and this x in the derivative equation to get a second equation, and then solve that system to get what C1 and C2 are. I'm omitting the steps here to keep moving here. So we get that C1 is 1 and C2 is 1/2. Okay, so this particular solution ends up being cosine of 4t plus 1/2 sine of 4t plus t times sine of 4t. Okay, so if you try to graph that, all the frequencies of everything here are all aligned at a circular frequency of 4. But there's a problem here because of this t, right? Because what happens when you graph that is because of this t, as time goes on, this term just gets bigger and bigger and bigger and bigger. It doesn't just keep oscillating in place, right? So if you graph this in a calculator, this just keeps going forever and ever. In fact, what will happen is the system amplitude will get larger and larger without bound until the system physically destroys itself. At some point, the spring will deform completely out of shape into a wire and it won't oscillate anymore, or something like that. Okay, this particular kind of a phenomenon is called resonance. Whenever you try to drive a system at or near its natural frequency. And of course, system designers want to make sure that you include damping, because if you have no damping, then if you either intentionally or accidentally drive the system at its natural frequency, then you will experience potentially catastrophic systems, right? This is like, you see this also in springs. Later in physics, when you study pendulum motion, you're going to find that pendulum motion behaves very similar to springs on a vibration. But instead of the mass moving up and down, it's the person swinging up and down on the left and right. It works very similarly. But you know what happens if you take a person on a swing? Let me kind of stretch what's going on here, right? What happens, you got a swing set and you've got a person here on a swing, sitting on a swing, right? And they're moving back and forth. So if I just lift this person up, if you're swinging your child and you let them go, what'll happen is their motion will oscillate, but eventually go to zero, right? You'll have a displacement around the equilibrium position this way of that, right? But how is it that children swing themselves? Well, what happens is they move their legs back and forth, right? And they move their body back and forth. So what's happening is they're applying a driving function that's very near the resonant frequency of this pendulum, the swing system, so that they continue. They're just right on the verge of going out of control, right? If they could do it consistently and there was no air resistance, of course there's damping, then they would swing more and more and more until they finally went around, right? But because there's air resistance and because they can't quite, they don't get quite exactly at the damping frequency, they can just maintain a kind of perfect balance between resonance and damping out, right? And so they can keep themselves oscillating, right? So swings are taking advantage of driving with your legs in your body position, a driving function that's near the natural frequency of the pendulum you're swinging on. Anyway, that whole phenomenon is called resonance. Okay, and I'm not going to show it here in the video, but there's a really good video if you can look at and copy this from the notes of a situation where resonance was really a problem. So there's a very famous bridge called the Tacoma Narrows Bridge that was built in Washington State, south of Seattle. I think back in the 1950s, maybe something like that. And of course, it's as hard as this is to think about motion in one dimension. In a bridge, things can oscillate in 3 dimensions, so the problem is even more difficult, right? But typically, bridge designers include lots of different kinds of damping to prevent natural frequencies from oscillating out of control. But there was this case when there was an unusually windy day, like winds of 60, 70 miles an hour, and it got this bridge, even with all the dampening that people built in, vibrating at its harmonic motion. And so it started deforming like this and swinging back and forth. Took about an hour, and then finally the bridge actually completely destroyed itself because so if you're interested in seeing the video of this, there's some old black and white video and some color video of this at this link. You can explore that. Of course, engineers, especially with computer-based modeling now, are very good at being able to test all frequencies at different levels to make sure that their systems don't exhibit behavior like this. Okay, there's another thing which can occur. I'm not going to go into a lot of detail here, but it's called the beat phenomenon. So, when you drive a system very near its, when you drive it very near its natural frequency, you can, without dampening, get resonance and kind of in increasing in amplitude. But if you drive a function where if you drive a system where the function is some multiple of or some integer fraction of the natural frequency, then you can, but not at the frequency, much lower. Like let's say that the natural frequency is 4,000 and you drive it at 4, which is an integer multiple of this. So there's 1,000 of these in this, right? 1,000 of these in this. Then it turns out that you'll get this kind of, it'll look like it's starting to go to resonance, and then it'll come back down to 0 again, and it'll start to go to resonance again. There'll be maybe 4,000 cycles in here, but then this green thing will be 4 cycles per second. And so you'll get what's called modulation, essentially. This is the basis of what we call amplitude modulation, which is how AM radios work. That you impose a much different frequency driving something at a much higher frequency. The reason why we use modulation, by the way, is that antennas are very efficient at transmitting radiation only at a quarter of their physical length. Like the wavelength has to be a quarter of their physical length. So you can't transmit like sound energy, which is in the, maybe only to 16 kilohertz because the wavelengths are too long. Antennas would have to be miles long. So what happens is you make an antenna that's a quarter wavelength at some giant frequency like 1 megahertz, like 1,000,000 cycles a second. That's this blue wave. And then you use a driving function with something called a modulator to impart that as an envelope that causes something like a beat frequency here. Okay, we're not going to go into this in more detail, but if you want to read a little bit more of that, I included one page out of another textbook that talks a little bit more about resonance and beat phenomenon in your notes. Okay, the one other thing I do want to mention is how this is analogous to any system where there's vibration and which energy can be removed through damping. So you can think of this mass spring here as we have something where forces are acting, so there's oscillatory behavior modeled by this, where we have a spring constant, we have a damping constant, we have mass, and then we have a driving function over here. And so this damping constant here essentially serves to remove energy from the system, which is why this dies down, right? If there's no damping, then it just goes forever, right? And just oscillates forever. So the damping represents anything that removes energy from the system, all right? All right, when it's down, if you think about it this way, when we pull the mass down, that means that we've converted some of the kinetic energy of motion into potential energy that's stored in the spring. Right? And then when the spring pulls it back, it's converting some of its potential energy stored in the spring back into kinetic energy, because engineers and physicists, they model things in terms of flows of energy. So if there's damping, some of that energy is removed. But basically what's happening here is as the mass is moving, it's changing form of energy, right? When the spring is stretched, some of the energy is stored in the spring as kinetic or as potential energy. And when it's moving, that potential energy has been converted to kinetic energy of motion. All right. So the reason I'm talking about that is there's a lot of other kinds of systems in physics and engineering that can be modeled this way, where you're moving energy from kinetic to potential energy, and there's some mechanism for draining energy out of the system. And one of those is electrical circuits that we mentioned before. Okay, if you have an electrical circuit, let's say we have a series circuit which has an inductor and a capacitor along with the resistor. Then we can use a second order linear differential equation to model that, where a current or charge flow through here is the independent variable. So in series circuits, right, energy is flowing charge, right? So it's leaving the source here. And if this is moving over time, that means that this charge can flow back and forth through the electrons are flowing back and forth through the circuit elements, right? So what's happening is the resistor has the same effect as damping. What this does is it just removes some of the energy to heat. That's what a resistor does. But coils or inductors, they can store energy in a magnetic field. And capacitors can store energy in an electric field, right? So what happens is as these electrons are flowing around the circuit or flowing back and forth through the circuit, right, their energy is being converted from storage in the magnetic field to storage in the electric field. Kind of analogous to how we're moving back and forth between potential energy in the spring and kinetic energy in the motion. Here, we're moving back and forth between energy stored in the magnetic field and the electric field. And then some of it is being bled off through the resistance as damping. And that, therefore, is the reason why you can represent a series inductance, capacitance, resistance LC or LRC circuit using this differential equation. So we have a second derivative term, a first derivative term, and then a variable term. The driving function over here is whatever is causing the voltage to change in a time-varying manner. So it's a function of time. The thing that corresponds to the mass turns out to be the inductance. The thing that corresponds to the dampening turns out to be the resistance. And the thing that turns out to be like the spring constant turns out to be 1 over the capacitance of the capacitor. Right, so all those same solution techniques we just solved, where you'd have 3 cases where you could have, under damping or critical damping or over dampening, or we could have resonance, or we could have beat phenomenon. All that kind of stuff applies to electrical circuits the same as it does to mass spring circuits. All right. Okay, so that is a huge amount of stuff to absorb in one setting, but hopefully that's enough to let you go ahead and start trying the problems in section 5.1.